We are taking question and answers on remote sensing system MCQs we are going to take. The first one is, which of the following doesn't indicate a stage in remote sensing? Remote sensing has certain stages. For example, the basic definition, it says it's a non-contact imaging. You are not going to go near the object, but still you sense it and know the characteristic attributes of that object. So which of these is not? So the answer is absorption of energy. It's not here, because remote sensing is what? Is the process of obtaining information without any contact with the object. So it has several steps because we need certain output. So we start with an energy source here. For example, let us take sun is the energy source. The transmission is going on. That is, whatever energy the sun has, the energy is transferred or sent or it travels. After this propagation of energy happens, interaction happens. So the interaction of energy with whatever object it is there. Then reflectance of energy takes place from these objects. There are certain multiple ways in which this happens, and then we transmit it, and whatever is being transmitted, we utilize it. And there are different types of images, data, what we get finally. So the absorption of energy, if the body absorbs everything, what do we get? We are getting nothing. So whatever we are getting either is the emitted energy or the reflected energy. The electromagnetic wave traveling from source to the object is having same wavelength. Let me show you here. First, there is a source of energy, and this light, electromagnetic wave, light basically, and it is coming. Now this is an object. This is a part of an object or certain object. Now the light is starting as lambda, some wavelength. Now the question is whether it will reach as lambda only. The answer is false. I'll just give you a small example. If we have sun and we have earth, so we have troposphere, stratosphere, mesosphere, thermosphere, exosphere. So there are different spheres here, different ion, molecules, everything is here. So these layers, this light or energy is going to interact with them, is going to change in some form. So the lambda is going to change somewhat. Okay. Which of the following indicates the functioning of a sensor? Sensor, simple word, is what? An instrument which senses something. So the answer here is sensitive to wavelength. So sensor is sensitive to certain wavelength. As I said, it is sensing certain wavelength, that is, it is not able to sense certain wavelengths. Certain part of electromagnetic spectrum it can sense. For example, IR it can sense. It may not be sensitive to the visible light. These are different sensor type: active, passive, scanning, non-scanning. All these are the types. So basic thing is that the sensitivity to certain wavelengths makes a sensor specific. That it is a IR sensor, it's a visible sensor, it's a VNIR sensor. So a sensor can be defined as electromagnetic instrument which serve as a path of recording and transmitting energy and sensitive to wavelength, and also give you the wavelength of that wave transmitted, so EIR or any electromagnetic part. Among the following, what indicates the correct set of classification of data? So all these things are mixed up here: analog, digital, binary, analog, vector, raster. And those who learn remote sensing with GIS, they will be tempted to answer D here. But what is the indication, the correct set of classification of data? So the first thing first is analog and digital, because there will be some camera, there will be some device which will take it. It can be analog, it can be digital. So the first step is this, then this raster vector can come later part. So as I said, whenever we have radiation reflection or whatever kind we accept, a camera can be there. Previously all the cameras were analog only. There was no discussion of digital 15-20 years back. But now everything is digital, almost digital. but still we have analog counterpart. That is why, because it was a camera, so we ought to have the analog to digital conversion because of the computers and because of the binary systems. So this analog data, digital data is the first set of classification, and after that you can have multiple classification, as I said, raster, vector, and binary, hexadecimal, or whichever form you want. But the initial start is analog and digital. The answer is A. The data obtained at the end of the transmission can be classified as analog and digital formats. One more thing, this raster vector, as I said, it will come later. It will be a classification. It is the classification of data only. Which type of remote sensing uses its own energy of electromagnetic energy? So some of them use their own source of electromagnetic energy, EM waves. Some of them not use their own. So source is sending its own energy and accepting the reflection or whatever is coming from that source. So, and the passive is, it doesn't send it. So active remote sensing is usage of its own electromagnetic energy, which emits and absorbs the reflected energy. For example, a camera, it is a flash. So it flashes, and when it comes back, that is recorded. In case of passive remote sensing, as I said, just camera flash. In passive remote sensing will not have this kind of flash. It will use some other source of energy. It uses some other source of energy. Normally, we have seen the sun is used in this all passive form. Let me elaborate it. This is passive sensors. These are active sensors. Active sensors are like LiDAR. So it is sending also, and it is receiving what it has sent. LiDAR. Radar also, it is sending and also accepting what it has sent. For example, LiDAR, VNIR spectrum, and radar, it goes to microwave spectrum. When we talk about passive, it is not sending anything, neither multispectrum nor hyperspectrum. LiDAR and radar are sending and taking, but these sensors, passive, are not taking. They are just taking what sun is sending them. Sun is sending, and after interaction, they are taking it. The correct sequence of transmission of electromagnetic waves in a remote sensing system can be given as I told you earlier also in the first question, but here I'll give you some other example. See, in the process of remote sensing, there are certain stages of getting the data, obtaining the output and the data. So there is the sequence. What is? We have an energy source. In this case, we have sun as the energy source. Then there will be propagation of energy, and there is now interaction of this energy with the object, and there will be some reflectance from this object of the input energy or which energy has come, and then this will be transmitted as a signal, and finally this signal, in this case our brain will decipher, send it to the mind, and then make a picture. So here the D answer. If you see two options, two stages are missing, but the sequence should be an energy source, propagation of energy, finally the interaction, reflectance, and the transmission finally, and getting the signal and making the image. Signal can be generated by. How can a signal be generated? Whichever sensor is there, whenever it gets something or some signal it will get, then only it will generate something. So here the answer here is A, interaction of electromagnetic waves with the surface. So these electromagnetic waves are interacting with these earth surface, and then the signal will be generated which are emitted from this surface, and it has certain spectral signatures, certain characters, certain attribute. For example, it can be a stone, it can be a nickel, it can be a diamond, it can be anything, a mud also. So everything has a specific signature, spectral signature, and this is how the interaction will give you a specific signal which will indicate a specific object or specific, you can say, the group of objects. Which among the following is the first Indian remote sensing satellite? This is Indian Remote Sensing 1A. This is the first Indian remote sensing satellite which was launched in mid-1980s. And this is capable of recording the reflected electromagnetic waves from the surface and transmit them to the ground station? The answer is C, IRS 1A. Among the following, the correct set of remote sensing classification can be given as. So remote sensing, how do you classify it? We already seen the data classification initially. So the final means the basic is active and passive remote sensing. So active will send its own, they have its own source of sending the data and the way of accepting or sensing the data, taking the data. Passive will only take it, do not send anything. For example, passive sensor will normally take the external source of radiation, which is the sun. If you see here multispectral, hyperspectral, they are taking the passive way of, the answer is B. The data obtained by the process of remote sensing needs great knowledge to understand it. Now this is quite a subjective question, that who doesn't know about remote sensing, can he be appreciating the data which is obtained by the remote sensing? Is it possible? The answer is not. A person who is well aware of the concept of remote sensing, surveying, satellites, everything is to be known, GPS, GIS. So sunlight you need to know, interaction you need to know, electromagnetic spectrum you need to know. That is science, physics, optics is everywhere. Satellite also you need to know what is its resolution, etc. Computer analyst, then you have to have antenna. The image is going to come. The image can be a thermal image. It can be a visible image or a multispectral image, means colored image or grayscale. All this information is to be needed. We are discussing remote sensing. In this remote sensing principles, we are taking MCQs. We'll try to understand this concept using these MCQs. The first is the relationship or relation between velocity, wavelength and frequency can be given as. So what is the answer here? The answer is B. How? Whichever wave you take, even if you can take a rope, you can see the waves in sea. All these have the same form like this. So this is how it travels. Energy propagates. If you want to understand this, we can have a mean line. A mean, this is a mean, and this wave is going up and down. The maximum extent it can go is amplitude. Two peaks, the distance between them are from two starting points where it starts or coming up or going down. So the distance between them, all these are wavelength given by lambda, wavelength. Now third thing is speed, velocity of propagation. And one more thing is frequency. 1 second, how many hops, how many ups and downs it creates or it travels. So this is higher. This is higher in 1 second, and more higher. This is the higher frequency, and this is the lower frequency because there is only one quarter of the wave. So this lambda equals C by F. If you write this and multiply cross multiplication, C will be equal to lambda into F. Lambda is the wavelength, F is the, or nu is the frequency. Next is remote sensing uses which of the following waves in its procedure. So whenever we do a remote sensing, that is, we are sensing the object, understanding the object without contacting it. So which waves are important in this case? The answer is electromagnetic waves. Electromagnetic waves, in this remote sensing uses these waves. First, the different waves present in the electromagnetic spectrum. We will be talking about the spectrum just now. So in electromagnetic spectrum, we have different lambda representing different frequency, and these are created by electro and magnetic field. That is, the electromagnetic fields, electric, that is current, which in normal language you understand, magnetism. So electric and magnetic field, because of this, the waves which create, if you see here, the electric field is perpendicular, the magnetic field is horizontal. These are orthogonal, that is, they are at 90 degree. So this is how the wave travels, waveform is generated, and this wave are electromagnetic waves. It's a big science by itself. So I'm giving you a layman idea, electromagnetic waves. In remote sensing, see, as I was saying, that there is an electromagnetic spectrum, that is the range of frequencies we have. and that is limited. So this range is a visible light beyond which you cannot see. For example, X-rays you cannot see, ultraviolet you cannot see, and the other waves also, infrared, you cannot see. You can feel the heat, but you cannot see the wave. That is not comprehensible by the naked eyes. The naked eyes can only see that part visible. Others are also there, and that can be sensed. Which of the following is not a principle of remote sensing? So, not a principle of remote sensing. The answer is interaction of energy with satellite. Though one form it is, but electromagnetic energy is definitely a principle. Even if you take this active or passive, so it has to send and receive passive, it has to receive some form of energy so that it can sense, it can image, right? Then the electromagnetic spectrum, as I said, the electromagnetic spectrum has different part. So some sensor, some satellite, they image in infrared, some in visible light, some visible range, some in say a different range. So other different ranges are there. So from here to here, it's an electromagnetic spectrum that I'm coming just now. Then interaction of energy with atmosphere is also important. See, the energy is coming from some source. It interacts with the different objects here. We have different layers: troposphere, stratosphere, mesosphere, and thermosphere and exosphere. All these have different ions, layers, formations, formulations. So this interaction of energy with atmosphere is there. So answer is interaction of energy with satellite is not a principle. It's not a principle. It is a process. It is a process definitely, but not a principle. Other three are proper principles of remote sensing. So energy is, interaction is not there. It's just a sensing. A if you say. Which among the following waves is having less wavelength range? Less wavelength range. I was trying to tell you earlier about the spectrum. Kilometer is a higher units. That is, 1 kilometer is around 1000 meter. Then of course meter is lower, 1 by 1000 of a kilometer. Millimeter is 1 by 1000 of meter, and nanometer is 1 by 10 to the power 9. That is, if you compare it with meter, it is 10 to the power 9 meter. Nanometer is 10 to the power minus 9. That is, if you divide meter by 10 to the power 9, then nanometer will come. So which is having the least one? Nanometer. Least is nanometer. This is the electromagnetic spectrum. Wavelength always increase from left to right. You can see also the wavelength is increasing. And the lambda, wherever it increases, the frequency will decrease. Because lambda is inversely proportional to the frequency. It is inversely proportional. So when, as I was saying, that there is a very small range of visible light which we human can see. There are so many animals which can see beyond this also. For example, the snake, it only senses heat. उसको केवल गर्मी दिखाई देती है. So he or it you can say attacks only because of the infrared. It has no eyes, normal visible range. In visible region, the blue light is having a wavelength range of. So we just talked about the electromagnetic spectrum. And if you see a small part of visible light, it starts with just prior to 400 nanometer and goes after 700 nanometer. This is the only range. And here we have every color. I'm just showing you blue, yellow, red, just to signify that blue comes first and red comes last. But if you see here, the left blue starts at 400 nanometer, just prior to 400 nanometer. This is 400 nanometer. And how to convert this into nanometer? See, nanometer is 10 to the power 9 meter, and micrometer is 10 to the power minus 6 meter. So just divided by 1000, it will be some 0.4 something, but it will just be prior to 0.4. It's A and B, A and C can be answered, but the actual answer is A. Others also you can see what is the range. Which of the following field is used by the electromagnetic waves? Which field? So electromagnetic name is electro and magnetic. So this already I showed you, electric and magnetic. So we don't have any other except electric field here. So electric field we are going to say it is the correct. See, Electromagnetic waves have two major sources of field, electric and magnetic. And as I said, they are orthogonal to each other. Electromagnetic, orthogonal, perpendicular to each other. This is a wave pattern which is formed because of the orthogonality. The electric components are placed in a vertical manner. This is electric, vertical. And this is a magnetic component. These are in horizontal manner. B, represented by B. And also we have arrow on E and B because that's a vector quantity. Among the following, which describes Stefan-Boltzmann formula? If you see here, I have an example also just to let you understand. The Stefan-Boltzmann law is basically based on the radiation produced and emitted by the body. That is, a body is creating, producing, emitting because it absorbs and then it emits. For example, a utensil making bread or anything which is heated, it will liberate, it will emit certain energy that is in the heat form. So this can be mathematically represented by m equals sigma t to the power 4. M equals sigma t to the power 4. And here we have this, of course, sigma, there is a constant here. So this one is the Boltzmann constant, T is the absolute temperature, and M is what? M is the spectral excitation of the body, how much it emits or the production is there. I'll give you an example to better understand this. For example, sun has a temperature, surface temperature as 5800 Kelvin. Its radius is 6.96 into 10 to the power 8. Calculate the power output. In order to power, you have to have an area also. So a sphere, the surface area of a sphere, the sun is a sphere. So 4 pi r square. The sigma we are using, as I told you, we are using this, and then T, temperature is 5800. So in this formula, we always use temperature in Kelvin. Which of the following is not a classification of scattering principle? Scattering is what? Scattering is whenever a wave or light, it interacts with certain object, it scatters, it changes its path, or has some formation. For example, lambda of this light, if the particle is smaller than it, equal to it, or larger than it, then the scattering will be different. For example, Rayleigh, Mie, and non-selective scattering. Non-selective means Mie scattering larger particles. So 3 types of scattering we know: Rayleigh, Mie, and non-selective scattering. But here we have Faraday's scattering, which is not the scattering which we know. So B, C, D are correct answer, which is not. So A is the correct answer. It is not the classification of scattering principle. Okay. Which of the following can act as an example of airborne platform? Airborne platform. Airborne is some platform in the air. For example, aircrafts. For example, you have a balloon. These are all airborne. If you go to water, it will be waterborne. If you are standing on the ground, it's say soil-borne or ground-borne. So at present we have airborne platform as Dakota, Aviaro, and Beechcraft. These are different airborne things you are able to see. It's like sensing from the place where you can see the ground, you can sense the ground. And the answer is Dakota, because these 3 MOS and these 2, they are not airborne, they are satellite borne. Polar orbiting satellite are generally placed at an altitude range of. So whenever we launch something, for example, ISRO launches or American Space Agency does it, they say PSLV launch, GSLV launch, that is Polar's satellite launch vehicle, and geostationary satellite launch vehicle. Why? The names are like this. This is because the answer is C, by the way. If you see it very closely, if you place anything in the orbit and that orbit length decides where, or the orbit diameter, or from the distance from the sun, Earth, that decides whether it is polar or geo. So if you see sun synchronous means you will see at the same time that satellite or that object every time at the same time at the place. The farthest is the geostationary satellite. That is around 36,000 we generally speak in order to remember it, but it is 35,800 kilometers. This is geostationary orbit. It has the same orbit time as Earth. Then we have the polar orbit, that is 200 to 1000 kilometers it is. Since this is an idea, but if you see in C, there is a range which fits with polar orbit. That is why the answer is C. In remote sensing and otherwise, what is electromagnetic energy? We'll try to know it through the MCQ questions. The first is, which of the following has the maximum value in an electric or magnetic field? So, first of all, this is the representation of electromagnetic wave. We have electric as well as magnetic field acting so that a wave is produced. So, what is the maximum value? So, we need to know the various aspects of a wave. What can be maximum? A frequency can be maximum, wavelength can be maximum, all these things are there. But with respect to this question, if the wave goes up, so the amplitude is increasing. And when we take the formula and the expressions, we see the amplitude play a major role. So here, which of the following has the maximum value in an electric or magnetic field? The answer here is D, amplitude, right? So in an electromagnetic field, the electric and magnetic field are present in form of waves in horizontal and vertical patterns. And in order to be present in that pattern, it is necessary to have maximum amplitude. These are the two patterns I'm saying, or the two orthogonal fields I'm showing you. So maximum will be the amplitude. I hope you got the idea. It's not wavelength, it's not focal length, it's not frequency. It's amplitude. Velocity of light can be given as light. So first of all, let us understand like this. We have sun. Now sun is very far off from us. But the light doesn't take much time to reach Earth. So if somebody knows how much time does it take, please give me the answer. And what is the distance also? I would love to know. The light speed is quite high, 3 into 10 to the power 8 meter per second. So these are 3 and 8 zeros. This is huge. This number is huge. This number meter, if I take 30 off, this much of kilometer, in 1 second the light travels, and it's a huge speed. So this velocity of light, I'll give you one more example. Whenever there is thundering and lightning, have you seen you see light first and then you listen and then you get to hear the sound of that lightning. This is because the vacuum air has around 3 into 10 to the power 8. It varies with water, glass and other medium. So it's 3 into 10 to the power 8. So the velocity of light we determine generally by using the electromagnetic wave principle, EM waves, and the Planck's law. So this helps us to derive a speed of light in vacuum. Approximately, this comes up to 3 into 10 to the power 8 meter per second. So just make it 10 and then raise to the power 8 meter per second. In electromagnetic waves, electric field is not used. So this is electromagnetic is electro and magnetic. So electric field is also there, magnetic field is also there. There is not electric field is not used, that is false. So the electro and magnetic E and B, they are orthogonal to each other. If you pass current, it will give you magnetic field. If you have magnetic field, if you move it, then you will be able to generate the current. So these are, E and B are quite say contemporary with each other, complementary with each other. So the electromagnetic wave field uses both electric and magnetic field. An electric field is placed in vertical manner and magnetic field in horizontal manner. Electric, magnetic. So this is a proper wave structure being formed. Again, let me tell you, these two are orthogonal. That is how we have a very different kind of wave structure which you see. So if you say electric field is not used, it is wrong. Even if it is there, the question would have been magnetic field, then also it is false. Determine the wavelength if the frequency is given 67 Hertz. So we have a formula, lambda equal to c by f, that is the speed of light, the speed is equal to lambda into of f. Lambda is wavelength and f or nu is the frequency. So we have two things known to us in this question. 67 Hertz is the frequency. 67 Hertz. Hertz is actually 1 by, it's per second. It is the name, it is named after Hertz. So 1 per second, 1 by second you can understand. So it's about second, 1 by second. Wavelength is lambda, so it will be in meter. Lambda. Okay. So you have this lambda, and since we have wavelength to be found out, lambda will be in meter. Okay. Now speed of light we know. Speed of light we know already. That is 3 into 10 to the power 8. 3 into 10 to the power 8. So we just talked about speed of light just now. Now apply it here. You have 3 into 10 to the power 8. So this lambda is going to be 3 into 10 to the power 8 and divided by 67. Divided by 67, and that is going to be meter per second. And that value will be 0. Because I'm just telling you that these unit also match. That is, the formula is also correct, and the computation will be like this. 67 will be the divisor. 0.044 into 10 to the power 8 meter will be your lambda, will be your wavelength. The answer is B. Find the value of energy if the wavelength is given as 43 meter. Now this formula you have to keep in your mind, because this is going to come again and again. This is E equals hc by lambda. So energy, we can represent it by Q also. Q. So hc by lambda. H is what? Planck's constant. It's a Planck constant. 6.626 or 6.625 into 10 to the power minus 34. It's in joule per second. And then we have this C is the speed of light, 3 into 10 to the power 8. Lambda will come in meter. Actually it's given already in meter, 43 meter. Energy will be in joule. So it is being asked in this question, find the value of energy if the wavelength is given as 43 meter. So just put the value 43 in the denominator in place of lambda. H is Planck constant. 6.626 or 6.6 into 10 to the power minus 34 for computation, and C is the speed of light, 3 into 10 to the power 8. So the answer will be D. D is the answer. 0.46 into 10 to the power minus 26 in joules. The answer will be in joules. So remember this formula, it's going to come up everywhere now. If the intensity of a wavelength decreases, the energy released will be Now, for a wave, what is the relationship between energy and wavelength? So we just saw this just in the previous question. If I write energy or Q, hc by lambda, hc is a constant. So hc doesn't matter when we have constant. So this lambda, if increases, energy decreases. If energy increases, lambda decreases. So it's an inverse relationship. I'm just saying if it would have an E directly proportional to lambda. So E increases, lambda increases, E decreases, lambda decreases. It is not the case. So E is directly proportional to 1 by lambda, inversely proportional. Okay. So this is A is the answer, increase. What will be the wavelength if the energy produced is 36 joules? Same formula we are going to apply here. Same thing. So E is hc by lambda. Now here, in place of E, you are going to put 36. In place of H, you already know, 6.626 into 10 to the power minus 34. Speed of light is 3 into 10 to the power 8. Lambda we need to find out. And lambda will be 0.55 into 10 to the power minus 26 or 10 raised minus 26. B is the answer. In an electromagnetic field, which field is placed horizontal? Sorry about that spelling mistake. So electric field and magnetic field, they are perpendicular to each other. Horizontal we have magnetic field, this, and vertical we have E, the electric field. Electric field and magnetic field, they are orthogonal. orthogonal. So what do we do? Gamma rays, first of all, gamma rays doesn't apply here anywhere in the question frame. Solar field also is not there. So electric field and magnetic field can be the answer. But horizontally and vertically, if you see the diagram and the animation, you can very well identify that which is going to be horizontal and which one is going to be the vertical. The wavelength sensed in remote sensing are. Now this is a very, it is covering a very huge answer. Because in case of remote sensing, the wavelengths are expressed in different numbers, different units, nanometers, micrometers range. Generally, it goes up to long length. But whichever way we take, we will always see in either nanometer or micrometer. If I say 26 nanometer, if I say 26 meter, so there is a huge difference between this. But we always take it in nanometer and micrometer. That is the answer of the question. So let me show you what we are talking about here. We start from one point in the electromagnetic radiation IR spectrum to the next part of the IR spectrum, and there is a whole bunch of range. The frequency is very small, and we have the amplitude of frequency which are very huge, like the radio waves. Radio waves even cross huge mountains. That is their wavelength. But ultraviolet, if you take, the wavelength is very small and the frequency is quite high. So there is a whole range and whole computation here that we need to understand what ranges we have, what numbers we have. So see here, this as I said, it crossed the mountain. Mountains can be in meters, kilometers, And if you say the smaller one start from the left side of IR spectrum, it is very small, very, very, very small, infinitesimal small. So this is the whole range. The highest is the radio waves, that is, we are talking about the wavelength. So this kilometer, we have the wavelength can be in kilometer, meter, centimeter, micrometer, nanometer. So we don't write in terms of kilometer. We don't write it in meter, centimeter. We only write it in when we talk about radio waves, etc. Micrometer is 10 to the power minus 6. Nanometer is 10 to the power minus 9. We also have 10 to the power minus 12, which is picometer. Because it is picometer is not given. Gigameter we do not generally use. Decimeter we don't use. We even don't use in meters. Okay. So the lower ones the question should be lower ones. So nanometer, micrometer. But the higher ones are in kilometer also and meters also. I hope you got the idea. The lower ranges are you'll always find the wavelength that are in nanometer, micrometer. You'll never find generally in terms of centimeter or millimeter, etc. That is what you have to use in the remote sensing perspective. Whenever you have the sensors and whenever you have to write certain ranges of visible range, IR range. Also, we have frequency ranges also. Gigahertz, megahertz, kilohertz. These are big frequencies. Okay. So that you can write. If you are a radio person or a microwave person, you will go to kilohertz, megahertz. This also happens. So C is the better answer here. C is the answer. Now in the following figure, capital X represent. So this is a wave. If you go to a sea, if you have a wave or by the rope. So these are the formation of the wave. It goes up from the mean. That is the amplitude. That is the amplitude. And from one hop means just assume maximum distance or minimum distance. This distance, so this is lambda. This is a wavelength. Then 1 second, how many hops it has, or how many times this wave you see. So this is a frequency. It may be higher, it may be lower. And the time period is 1 by frequency. Frequency is in hertz, which is simply 1 by second. This is 1 by time. So X is what here? Wavelength. Lambda is the answer. Lambda. Right? The correct answer is D. Remote sensing, electromagnetic spectrum. So we are going to do MCQ questions, objective questions on this. First is energy of the discrete particles can be given by. So we have a wave that can also be understood as photons. Photons. Light as energy, light as photons, and as waves. So if you go to say seashore, you'll see waves. So energies are passed on. Also momentum will also be there. So The answer is photons actually. So photon acts as a constituent particle if we talk about electromagnetic waves. So because it has certain attributes or properties like energy and momentum. So one photon is equal to one packet of light, which is able to deliver it to the wave and also helps us for certain classifications. So photons come in discrete. Discrete means you can divide them. You can discern them. So discrete particles or packets of energy. These are the packets, and these are transferring the energy. And this is how momentum is being transferred. That is how a wave is produced. This is a simple example of a wave. So if we take 2 peak, that is the wavelength, and 1 second, how much it travels? That is your frequency. Which among the following is having more wavelength? So this is an electromagnetic spectrum. I'll show you one more, and I'll just reverse this. So if you see here on the right side, this wavelength is 10 to the power minus 18, which is very, very small, very, very small. And the frequency is 10 to the power 26, which is quite high. And if you take the left hand side, the wavelength is very high, 10 to the power 8. These all are in meters. And frequency is very low, 10 to the power 0, that is around 1. 1 wave per second, this kind of. So the wavelength, if you see, it varies, and lambda is minimum on the right hand side, frequency is maximum. So which among the following is having more wavelengths? So here you have radio waves, high wavelength, 10 to the power 8. Then comes microwaves, then infrared, ultraviolet, X-ray, gamma rays. The lambda or the wavelength is minimum. They are very small and very, very close. The frequency is quite high. So lambda minimum, F maximum. So radio wave possesses the longest wavelength. In the electromagnetic spectrum, we have a formula C equals F into lambda. So which makes it suitable for this classified radars for operating in a particular region. F is actually inversely proportional to the lambda. So wherever frequency is high, lambda will be less. Wherever we have lambda high, frequency will be less. So the radio waves is going to be the correct answer here. Which among the following wave is not employed in case of remote sensing? Now, the small wavelength, these are absorbed by the atmosphere. So this sensor, whichever it is mounted, can't use this facility which can be provided by these rays, and they are very less. So this is making a sensor is also one of the challenge. So here we have, first is the, of course it will be atmosphere absorbed, and those gamma rays, we start from the right hand side. The gamma rays, we don't use it this X-ray also we don't use, ultraviolet also you not use. We start with IR, and then we have this IR, microwave, radio, and also in this we don't use everything. There are certain atmospheric windows. We can't use all these. So there is in these windows where we can use. So there are different sensors with different wavelength and frequency parameters. Optical mechanical scanner is used in which type of electromagnetic waves? So we have thermal IR. So if you see infrared region, we have 2 regions we can divide it, or classified: thermal IR and the reflected IR. Thermal IR and reflected IR. That is one which is reflected, one is it absorbs and then emits, body absorb and then emits. Thermal IR. So the thermal IR is equipped with the optical mechanical scanner and a special system which is free from a film, produces image by using the wavelength of range 3 to 5 micrometers. So this is what we are talking about, thermal IR. This is the range. Radio waves are having the longest wavelength among all the electromagnetic waves, and this is absolutely correct, true. So you have a radio station or a television station, and you are here. You are able to hear everything. You are able to broadcast and telecast. You are able to see and hear, because it is able to clear a big mountain. It is able to clear the buildings, etc. So this is true. Here we have the wavelength quite high, frequency less. Gamma rays are having a wavelength of dash. Now the answer here is C, but it is not also correct. Why? I'll just show you. Gamma rays, the range is what? somewhere 10 to the power minus 12, it goes up to 10 to the power minus 18, right? If you come to the left, the wavelength is quite high, frequency is less. So whenever we talk about gamma rays, we are talking about nanometer, this place, nanometer. So this is 0.03 nanometer, it is less than, it's correct, because the answer questions is such that less than, then this is correct. Which of the following waves can be used in case of remote sensing? So of course we have seen ultra, UV, X, gamma we cannot use, because if you see your camera or a mobile camera, you employ the sunlight or use these lights which are there, artificial light. So electromagnetic spectrum, we have different kind of classification, and there are certain places where the content or the rays are absorbed by the atmosphere, and most of them are used in remote sensing. These visible, IR, radar and radio waves we use. UV, X and gamma we cannot use because the frequency is also very less and the lambda cannot be used for that. Which of the following indicates the correct set of combination of radio waves? So it's quite clear because we have discussed the spectrum. Radio waves, very high wavelength and very low frequency. Wavelength is too much. So too much means longer wavelength and less frequency. So answer is B. The answer is B. Now the question would have been, say, gamma rays. So the first would have been correct, shorter wavelength and high frequency. Because you cannot have shorter wavelength and shorter frequency and longer wavelength and longer frequency. How much wavelength is reflected back by the Earth's surface from the absorbed sun radiation? So this comes under the Earth's energy budget. So what is the incoming solar energy? How much is reflected? How much is reflected by the clouds, atmosphere, Earth's surface? All these idea you can see here. Some land and oceans are also there. So they are absorbed by land and oceans, around 51% it is. Now when we talk about wavelength, the answer is B, 0.5 micrometer. This is the answer. The radiation received from sun is distributed all over the world in a manner that the entire radiation is useful. But some of this is reflected back, which is 0.5 micrometer. So the answer here is B. B is the answer. Okay. As I said, you have to have this idea about Earth energy budget to know this content. EM wave varies from dash to dash. Now if you see, it varies from kilometers to less than this picometers, right? But the EM wave is a continuum of energy. Right side, if you see lambda is maximum, frequency minimum, because I have changed that electromagnetic spectrum. So if you say nanometer to micrometers, we start with 10 to the power minus 9 and 10 to the power minus 6 we stop. Is it the whole range of electromagnetic waves? No. 10 to the power minus 6, 10 to the power minus 6 is somewhere in between IR, this spectrum, EM spectrum. Because we are talking about what? We are talking about whole. So we have to take the maximum range. Centimeter to nanometer, we have meters also, kilometers also. So D is also incorrect. Nano to micrometer is absolutely incorrect. Now the A and B is meters to nanometer, meters to micrometer. So meters is okay, but nanometer, micrometer is lower. So go up to nanometer. Meter to nanometer is correct. Because we are taking the left and right maximum values, maximum lower value, maximum higher value. This is how meters to nanometers. If it would have been kilometers, then also we would have taken kilometers, right? The formula of energy produced from the body can be given as, so this is E equals hc by lambda, this is Q equals hc by lambda, okay, and h is Planck's constant, c is speed of light, lambda is the wavelength in meter, so energy in joules. So Q is hc by lambda, the energy propagated from the body. In remote sensing, we are discussing solar radiation. We are taking the MCQs based on it. We'll try to understand the concept using the MCQ. The diameter of sun can be given as. What is the diameter of the sun? It's 1392000 kilometer. That is 1.39 into 10 to the power 6 kilometers. Now sun, as we know, is the most important and life-giving star for us, for our world, which we know. There may be others also, we don't know. So the radiation which are emitted by sun, we use in the case of passive remote sensing, because we have sun and we have earthly materials. It can be anything. So wherever it reflects or emits, the satellite, airborne, or whichever way, we sense it. So this sensing of rays coming from the sun is important to us. So I wanted to show a relationship between Earth, Jupiter and Sun. Earth has because this is the diameter, 12756, Jupiter is 142800, and Sun diameter is around 9.7 or 10, you can say, 10 times the diameter of a Jupiter. So you can say Jupiter is 11.2 times the diameter of the Earth, and the Sun is 9.7 times the diameter of a Jupiter. The energy radiated from Sun in visible region will be around. So sun rays, sun energy has all the different content. So the sun energy or the rays which are coming will only be in visible range? Only be in visible range? No. Electromagnetic spectrum, it starts and ends, it has a very wide range. It starts with ultraviolet and before that also, and then goes up to radio waves, big radio waves. So the ultraviolet frequency, very high frequency it has, and the radio wave frequency is small, but there is very small portion which is a visible portion, and this is only what we see, right? And this portion in whole of the energy which is coming from the sun, this part is seen. Which is that part? That is 43%. 43%, if 100% energy is coming or rays are coming, 43% is visible. Others, that is 47-48% around, is of different places in the spectrum, and mostly in the IR region, the infrared region, because you can feel the heat of the sun, and because it's like a fire, sun is like a fireball. So mostly we have in the heat or IR region or thermal region, you can see. The value of solar constant can be given as solar constant. So solar constant, first the answer is 1367 watt per meter square. So this is a radiation received per square meter of the atmosphere at incidence angle theta equals to 0. So whenever an energy comes, we are not talking about one place, because sun's energy comes at some place directly, some place it doesn't, mainly in the pole area. So the energy received from the sun, this can be distributed all over the surface of the earth, right? Because we have to take the average. And when we take the average incident flux density, this is again a value, we can find out how much average incident flux density is there for whole earth. And there is a constant, this is called 1367. As I said, we represent it by capital G along with this small SC, solar constant. This is a radiation received per square meter, watt per meter square is the unit you see, of the atmosphere at an incidence angle theta equals 0. When the earth is at the mean distance from the sun. So it is at the mean distance from the sun. Theta, first of all, theta has to be 0 incident angle, and earth is at the mean distance from the sun. Now solar constant, as I said, 1367 watt per meter square. There are certain things which we need to know. It is a mean value. It's a mean value. As I said, everywhere we have different energy. First is the orbit of Earth. Actually, our orbit of every planet around the sun is in elliptical orbit. It is not circular. And the distance, that is why the distance between the sun and Earth, it varies. It is not always constant. It is around 3.3% it varies. So as I said, 3.3% it varies, and the distance varies because of the elliptical orbit, it's not circular. And the solar irradiation, this also varies over the year approximately. That is why we are having this average constant value, which is 1367 watt per meter square. Temperature of the sun is around. What is the temperature of the sun? So we have seen about this just now. So sun, this is, as I said, the most valuable, not vulnerable. It's very most valuable among all the stars because it gives us life and is said to emit a lot of radiation, different radiation as we saw, 43% in the visible range. So in order to get this radiation, emit such kind of radiation, it has to have a very high temperature. It must possess a large amount of temperature. You know the distance of Earth from the sun, and with all that distance also we can feel the heat, especially in summers. We cannot stand outside. So it's 5750 to 6000 Kelvin. This is the correct answer. D is the correct answer. So we have 15.7 million Kelvin at the core of this solar interior I'm talking about. And then we have the radiative zone around 7 million to 2 million. Then we come to convective zone, outside layer, 2 million K. And the final layer, which is the photosphere we call it. That is the temperature we're talking about. Around how much percentage the incident radiant flux can be absorbed by the materials present on Earth? So whenever some light or energy comes, some bodies they absorb and then emit. So that absorption is being asked here. So sun radiation is coming to the Earth. In between it is being absorbed. On the Earth also it is being absorbed. There are different phenomena taking place, right? I'll show you this phenomena just now, but just understand that this is an incident radiant flux we are talking about, and it is absorbed by materials which are present around. There are different materials. So as I said, the radiation which is being spread around all over the world is said to possess an incident flux density solar constant 1367. So we can divide it into certain class in which 48% of this is absorbed by Earth's surface material. 48% is absorbed by the Earth's surface material. Okay, I hope you got the idea. So it can be a stone, it can be some material, it can be sand, it can be buildings, whichever, right? So let me just show you here. Here we have extraterrestrial radiation. It is coming. And then we have the atmosphere. Atmosphere here. It is absorbed. These lights are absorbed. And some are reflected, some are scattered, some are absorbed. All these phenomena is taking place. See, if you see they are absorbed, lost 11 to 30%. Scattered 1.6 to 11%, scattered toward 5.26 5 to 26%, and all these direct to the Earth, it is around 83 to this percent. Determine the spectral existence of a black body if the absolute temperature can be given as. So we have a formula here. We have Stefan-Boltzmann law. Stefan-Boltzmann law, and it will give you the spectral existence of a black body. So black body, it is assumed that it absorbs everything and it emits everything. That is what the idea is. So for that we have, because capital M equals sigma T to the power 4 is actually the Stefan-Boltzmann law, and we can apply it here because the value of temperature is given and sigma is a constant here, right? It's a constant. So we know this constant sigma, okay? And then 300 is the temperature in Kelvin, it is being given. So we apply it here, we multiply it here, and this is going to be D. D is the correct answer here. So some graph also I tried to show. These are the graphs. Find the value of lambda if the temperature of the body is given as 560 Kelvin. Temperature of the body is given T, capital T is given. We have to find out the lambda. So in order to equate or have a relationship between the wavelength and the temperature, so Wien's displacement law is lambda equals A by T. A is Wien's constant, which is 2.89 into 10 to the power minus 11, and we can apply it here because temperature is also given, and lambda can be found out, and lambda will be the wavelength, which will be in meters here, because this is Wien displacement law, because temperature is given 560, you can apply. This is going to be 5.16 into 10 to the power minus 14 meter. C is the correct answer. So you can again understand here with this temperature and the lambda, because if you multiply the wavelength and the temperature, they will always be a constant. That is how this graph is having a say pattern, proper pattern, you see, bell-shaped, almost bell-shaped curve is there, because lambda into t will always be a constant. Determine the spectral excitance of a body by using the Planck's law. It has to have a C here. If the wavelength is given as 456 meter and the absolute temperature is 765 Kelvin. So we are going to apply the Planck's law for this. The Planck's law for this particular question is m equals C1 divided by lambda to the power 5 into e to the power C2 by lambda t raised to the power minus 1. In Planck's law, C1, C2 are radiation constant, so we don't have to worry about this. And lambda, you are going to put it here. Lambda is also given 456 meter. And temperature is also given. You have 765. You just put it here. And there is slight change I am going to do. 765 you are not going to write here. You are going to put here because it is a lambda, 456 meter you are going to put. So this m, which is the spectral excitance of a body, using the Planck's law will be 3.6 into 10 to the power 30 watt per square meter. These constants are unknown to us, C1 and C2, so don't worry about that. The answer is A of this. Determine the absolute temperature of a body from Stefan-Boltzmann law. If the spectral excitance of a body is 3.55 into 10 to the power minus 10 watt per square meter. So we know Stefan-Boltzmann constant, we have already used it in earlier question, m equals sigma t to the power 4. Since m is known, it is already given, spectral excitance is already given, and then sigma is a constant, we know this constant, and temperature t to the power 4 t you want to know. So by this you have B as the answer, 1.58 K, that is the Kelvin. Temperature will come in the Kelvin. From Wien's displacement law, determine the absolute temperature if wavelength is given as 0.05 meter. So lambda is A by T, we have already seen in one of the questions, Wien's displacement law, and we have lambda here 0.05 meter. Constant is already there with us, 2.89 into 10 to the minus 3. Temperature can be found out, it is 57.8 into 10 to the power minus 3 Kelvin. D is the correct answer. In remote sensing, we will talk about sensors through the questions. So we have different satellites, we have airborne platform, there are sensors on board and they will sense the electromagnetic energy. So the question is, strength of signal doesn't depend upon which of the following factors. So the answer is reflection. That is, whenever we are talking about any signal, the power, the intensity, all this, it depends. First is energy flux, dwell time, altitude. All on this it depends, but reflection, it doesn't depend. So a signal can have the capacity of recording and displaying numerical data on an image. And basically image is what? It's a two-dimensional array of values, radiometric values, or you can say the digital numbers. This is an image. So it depends on the energy flux, altitude, spectral bandwidth, dwell time, and also IFOV, instantaneous field of view. This is all is there. Let me tell you again, depends on energy flux, altitude, spectral band, width and dwell time, and IFOV. So if this is your satellite, say, or any platform, so this signal depends on all these. The strength depends, but reflection, it doesn't depend. There is energy flux, we are going to discuss it in the next few coming questions also. The energy flux is the amount of energy reflected or radiated from a terrain. That is, it is lower and higher depending upon whether it is a darker day or a brighter day. So I'm just giving an example of energy flux, how this affect this signal. Just taking an example. Similarly, dwell time and altitude are also there. Which of the following indicates the correct set of bands operated in LIS-3 satellite? So LIS-3 is not a satellite, LIS-3 is a sensor first of all. So LIS-3 is standing for linear imaging and self-scanning. LIS is this linear imaging and self-scanning. So this is a sensor, and when we talk about LIS, there are bands green, red, and green, red, NIR, near infrared and short wave infrared, SWIR. The swath is around 141 kilometer, and resolution, that is 2 points, they can be resolved on the ground, is 23 meter. So visible ray and NIR. So first one is the correct answer, because green and red comes in visible, NIR is already there. Because the NIR radio B, C, D, they don't suit the answer. So whenever we talk about LIS 3, we need to understand LIS 4 also. So these are different bands of LIS 3. So there are LIS 4 sensor also, you understand, So LIS 4, LIS full form remains same. So it can work either in panchromatic. Panchromatic is basically, pan means total, whole, and chroma. For layman understanding, just understand black and white. It's not black and white, it's basically grayscale image, just understand like this. Multispectral is colored image. So it's not having SWIR, except SWIR. So either panchromatic, multispectral mode, it will work, same bands as LIS 3. SWIR is not there. Okay. And resource set, if you see, the swath was 23.9 in a multispectral mode, and panchromatic mode, this swath is 70.3. That is the whole area it can see, it can cover. And resource set 2, the multispectral swath is enhanced 70 kilometers. So if a satellite is there, so the range it can see is this swath at one time. We have this linear array sensor. This can be also steered angle. It can be moved like we steer car. We have a steering like this, 26 degree across track and along track. So this is across track, not along track. And this also enable the stereoscopic imaging. So panchromatic is resolution is 5.8 meter, 5.8 meter. This is very good. 5.8 is really good. And swath I told you. So swath also we have the panchromatic resolution is 5.8, and we have multispectral. There is no SWIR. Please remember, only this GR and NIR is there, and same spectral range is same. As I am saying, the resolution is 5.8 meter. LIS 4 is quite good. Energy flux may affect which of the following? Energy flux, as I told you, energy flux is what? Whenever there is an object, there is a surface. So that is the rate of transfer of energy or speed of that transfer. How far or how fast it travels through that surface. That is energy flux. So total rate of energy transfer, that is joule per second. That is energy per time. Joule per second. There is one more thing, specific rate of energy transfer. We normalize it for a unit area. That is watt per meter square. What is what? Joule per second only. Joule per second is what? Because energy per unit time is power. Power is what? Watt per meter square. Okay. So watt per meter square. Watt per meter square. Okay. So this is how you can understand energy flux. Energy flux. Now you understood this. So these are different ways it can be taken. This energy, this is called as energy flux density sometime. Let me tell you the answer, then we'll discuss more. Energy flux may affect the strength of the signal. Strength of the signal. Just the value of the energy flux will affect the strength of signal, as they are interconnected. They are interlinked with one another. They are interconnected. Okay. And along with this, not only energy flux, the altitude, spectral bandwidth, this also affect the strength of the signal. This also affect the strength of the signal. So along with this, not only the energy flux, so we call this energy flux density there are different definitions. So radiative flux, heat flux, sound energy. These are special cases of the same term, energy flux. Okay. Which of the following can merge the imagery of LIS 3 and PAN? LIS 3 and PAN. So LIS 3 and PAN, I already told you. So IRS multi-sensor. So IRS multi-sensor has this capacity to merge these. Let me tell you what is merging of these, why do we require it. LIS 3 and PAN. PAN is grayscale. As I told you, in layman you can understand black and white. It's not black and white, but grayscale you can understand. And color image. So when you have this grayscale has a better resolution, but color has a good look, but not a very good resolution. So why not to combine the good resolution with the appearance of black and white? So we merge them. So we have a good, we get the good image, good quality image in better resolution. So it has the better resolution. Quality is will also be good, of the output will be good. So IRS multi-sensor is the answer. Okay, list 3 and PAN just I gave for your reference. So list 3 23.5 special resolution, PAN is 5.8. So you apply the 5.8 meter along with the power of that color which this 3 color image has. So these are spectral resolution. Spectral resolution is what? 4 bands, list 3, 1 band, PAN. And radiometric resolution, you can assume it to be 0 to 2 to the power 6 minus 1. This is the range. The different gray shades will be there. Which of the following indicates the correct expansion of WIFs? WIFs is what? Wild field sensor. Wild field sensor, WIFs. So the answer is A. This A you can correct. So this is the expansion, wild field sensor, and IRS-C, IRS-1C, 1D. And these two satellites are already non-functional now. But these WIFs were there. So just to know that what was WIFs, etc., you need to know. So as I said, IRS-1C, 1D, it was this payload was on board this, and it has 2 band operating in a visible role in the determination of object specification. So as I said, 2 band operating in visible and NIR. So 2 bands are the visible and NIR. So this is what I am talking about. These are the bandwidths. Swath is 812, and this 7 bits quantization level, 0 to 7 to the power 7 minus 1. This will be the different shades here. And SNR is also okay. IRS-P3 satellite uses which of the following sensors? IRS-P3. So MOS. This modular optoelectronic scanner having a wide range capacity is mounted on this IRS-P3. We'll talk about IRS-P3 just now. And for what importance does have, what importance it is, this satellite is having a very wide coverage capacity. Okay, because of this modular optoelectronic scanner, right? So we have 2 sensors here. One is WIFs and one is MOS. WIFs we already talked about, wild field sensor. PAN sensor uses 2 band operators. No, this is incorrect. It's false. We already seen that PAN is only 1 band. Okay, grayscale we take only 1 band is there. So panchromatic sensor is placed on the boards of IRS-1C, 1D, which are, as I said, dysfunction, non-functional. This is having the capability of handling only 1 band, which will be any of the waves in this EM spectrum. You see here, the PAN is important and only 1 band. This is what we are talking about. If you talk about list 3, it has 4 bands. While mapping land use and land cover, which scale is recommended? So whenever we make a map, we need to know the scale. So what the distance on the map and distance on the actual ground. For example, you have say 1 centimeter or 5 kilometer ratio, or let me tell you that 5 kilometer you are representing by 1 centimeter on your map, or you are representing 10 kilometer area or range in 1 centimeter on your map. So the ratio is going to be the scale. That is called the scale. So this the better idea for mapping land use and land cover, better way, what is the scale? Is it 1:25? That will not be working. This is just an image of a Dehradun area. So this 1:25,000 scale is the best one, the better one. This is the mapping of land use and land cover is done so as to have a detailed description about each and every aspect. And for this scale of this 1:25,000 scale is recommended as it gives us a better visual, better appearance and better details. 1:25,000 is the answer. The sensor used in the digital elevation model can identify contour heights greater than. First is, what is contour? What is digital elevation model? So these contours are basically the lines which are at the same height. So if you see these 2 points, they are at equal height from the mean sea. Okay. So these are called contours. So every sensor has the capacity to record and display information that we know, and the display of information is bounded by certain limits. So the limits it being asking, we are talking about DM, digital elevation model. So we can find out DM through this contour, through this DM, and we just have certain points. We get certain height points, and through height these center points or height points, we can extrapolate, and for the curve fitting can be done, and we can get the digital elevation model or the 3D view. Okay. So here we have 10 meter is the answer of this question. 10 meter is the answer. 10 meter. The sensor used in DEM can determine the object higher or it can height greater than 10 meter. Now IRS-1A and 1B satellites can carry which of the following sensor? So I1A, 1B, as I said, they are non-functional. So the satellites RS-1A or 1B may have this list 1 and list 2 sensors. We already talked about this, and they are mounted on these on board. So let me tell you about list 1, list 2 also, because we need to know what has happened and where we have reached. So list 1, list 2 is given here. IRS-1A, 1B, way back 1998 IRS-1A, then 1991 IRS-1B. These are 4 bands: VGR, blue, green, red, and NIR. List 2 is also same as list 1. And if you see, the spatial resolution was 72.5, and list 2 it was 36.25. So it has increased, and after that also it further increased when we had IRS 1C, 1D. It further increased. Okay. Then if you see, there are different other satellites also, important satellites. After RS-1A, 1B, P2, 1C, 1D, then P3, P4, P6, P5, Cartosat 2. Okay. And these are resolutions which, if you want to have just a reference of this, you can assume that Cartosat 2 resolution, the 2 points which are discernible or resolvable on ground, it's around 1 meter, and that's very good. 0.8 meter. It's quite good, appreciable. 0.8 meter. And after that also we have various other satellites which gave us a very, very good resolution. I'll just show you some of them which just we know that they have come. These are the recent one. If you have to have a look, these are Earth observation satellite, and it's in which orbit also it is being seen. It is being shown here. December 11, 2019, it's reset. And Cartosat 3, Cartosat 2B, all these are, Cartosat series was there, ResourceSat series is there, in different resolution, and all these were these satellites which we talked about. So this is all about the sensors. Thank you so much. Take care of yourself.